a vector field up here, and then I've got this problem. I say I want to evaluate this work integral from -1,4 to -2,5. Now that looks weird. Okay. When you see a problem written like this, and it is correct to write certain problems this way, that's essentially a dead giveaway that f is going to be a conservative vector field, because otherwise this problem wouldn't be well defined. But if I'm saying I want to be able to integrate from this point to this point without specifying how I'm getting there, I'm sort of implying that it doesn't matter how I get there. Okay. So I'm pretty sure that this is going to be a conservative vector field. However, the fact that it's written that way doesn't absolve you of the responsibility for proving that it actually is a conservative vector field. So that's the first thing that I need to do. Prove that this is a conservative vector field. Otherwise, this is just a nonsense problem. Okay. So I'm going to give this a name P, and I'm going to give this a name Q. I'm hoping those are the partials of some potential function. I do want to remember that in order to be able to conclude that I have a conservative vector field, I have to be working on a simply connected region. And if I take a look here, I've got a slight problem because the domain for this function is not all of 2 space because I've got that x in the denominator. So the domain of this problem would be everything except the y-axis, because that's where x would be 0. So the domain really is in 2 pieces. There's everything to the left of the y-axis, and there's everything to the right of the y-axis. But the domain of this function isn't even connected, so it can't possibly be simply connected. However, I can see that this domain, like we said, is made up of 2 parts. I can tell which part I care about for this particular problem. I want to be going from -1,4, which would be over here, to -2,5. Those are both on the left-hand side of the graph. So I'm going to define D to be the set of all points x, y, such that x is strictly less than 0. That's this region that I've shaded in blue over here. And I can say that D is simply connected. I mean, I can just look at it and see no holes. Now, if I were working on the right-hand side is also simply connected. So I could make that argument, but I'm not working on the right side. I'm working on the left side, so I'm going to go ahead and say that the left side is simply connected. Okay. And now, if I can show that this equation of some partial derivatives being equal is true, then I'll be able to say that f is conservative on this region D, which is the left half of the plane. Okay. So remember, if this is conservative, P is already the partial of my potential function with respect to x. So I want to take the partial of it with respect to y if I want to get to a mixed partial. So we're taking the partial with respect to y of 2xy plus 1 over x. And that's just going to be 2x. There are no y's in this term, so it just drops out. So then I'm going to take the partial of q with respect to x. So that's the partial with respect to x of x squared minus e to the y. And that's 2x. Those are the same. So since these are equal on a simply connected region, f is conservative on D. Okay, excellent. So now for evaluating this integral, I've got a couple of options. I now know that this integral is going to be independent of path. So if I wanted to, I could just draw a path going from this point to this point, as long as that path does not cross the y-axis so that it stays in D, I could just parameterize that path and integrate. So I could draw the straight line path going from here to here, and I could parameterize and integrate. That would be perfectly acceptable. I'm going to do it a different way because I want to find a potential function. Because I know that when I have a work integral like this, where it's independent of path because it's conservative, the vector field is conservative, I'm just going to get the potential function at my ending point minus the potential function at my starting point. So I'm going to find the potential function and evaluate this integral by just evaluating that potential function and then subtracting. Is that easier or faster than just parameterizing that path? I don't know, but that's a skill we haven't learned yet, and that's a skill I want to learn. So let's take advantage of the opportunity and learn it. That was not a coronavirus cough. That was me swallowing wrong. Oh, I do hope everybody is staying healthy. Okay, so how do we find a potential function? And I will just tell you, those of you who are in differential equations or who've had differential equations, this is going to feel very, very familiar. It's very similar to what we do when solving exact differential equations or when working with Hamiltonian systems. Okay, so essentially I now know, because I've proved that it's conservative, I know that P is the partial of f with respect to x, and I know that Q is the partial of f with respect to y. Once I've proved it's conservative, I can write that. Until I've proved it's conservative, I can't. I'm just kind of hoping that that's true. Okay. So if I want to find my potential function f, I'm going to do this as step 1. I'm going to integrate either this function with respect to x or this function with respect to y. So step 1, integrate. And it'll be either integrating p dx or integrating q dy, because of course if I'm integrating p, I'm integrating the partial of f with respect to x, and if I'm integrating q, I'm integrating the partial of f with respect to y. So I'm taking an antiderivative of the derivative, which should give me a partial formula, because I'm only integrating a partial derivative, a partial formula for my potential function. Okay. So it really doesn't matter which one I pick. I think I'm just going to integrate p with respect to x. Okay. So I'm going to say f is an antiderivative of the partial of f with respect to x, integrating with respect to x. So that's going to be integrating 2xy plus 1 over x dx. So I'm integrating this now with respect to x. So y is a constant. So here I'm going to get x squared y plus the natural log of the absolute value of x. Absolute value is going to be very important because I've got negative x values. So if you are one of those people who is sloppy about the absolute values that you get when you integrate 1 over x, shame on you, and don't do that ever again. Okay. All right, and then plus a constant. There's my constant. I was integrating with respect to x, so I was treating y and any function of y as a constant. So my constant of integration, I can't assume is just going to be an honest to goodness constant. It's something that, for the purposes of this integral, I was treating as a constant. So k of y is going to be a function of just y. There are no x's in it, but that will make it constant with respect to x. So that gives me a partial formula for f. I've got two terms that I know exactly, but then there's this third term that depends only on y, and I don't know what that is yet. So I've just got a partial formula. Okay. So I haven't yet taken advantage of the fact that I know that q is the partial of f with respect to y. So I'm going to take advantage of that now. So step 2, I want a better marker. Okay, step 2, differentiate with respect to the other variable. So I just integrated with respect to x, so the other variable is y, set equal to the other component function, and solve for, in this case it's going to be k prime of y, and I'll just write or k prime of x if you integrated q with respect to y in step 1. Okay, a lot of words, let's see what we mean. Okay, so I know that f of xy is x squared y plus the natural log of the absolute value of x plus some function that depends just on y but not on x. All right, so I'm going to take the derivative of this, the partial, with respect to y. So when I do that, I'm going to get x squared. This term drops out, plus k prime of y. Now here, this is the one place in this problem where it's acceptable for me to use prime notation. When I'm taking partial derivatives, we don't use the prime notation because we have to have a way of indicating that we're taking the derivative with respect to a particular variable. But here I can, because I know that k only depends on y. Okay? So this is a full derivative with respect to y. So this gives me a formula for the partial of f with respect to y. But I have another formula for it as well, because I know that q, which was the second component of my vector field, and oh dear, what was that? That was x squared minus e to the y, is also the partial of f with respect to y. So I now have two different formulas, but they've got to be equal to each other. So if x squared plus k prime of y is equal to x squared minus e to the y, I can subtract an x squared from both sides, and I get that k prime of y is negative e to the y. Okay. So I took the derivative, set it equal to the other formula for the derivative that I had, and that allowed me to solve for this one piece that I didn't know. Notice this only depends on y. There are no x's in it. If you are going through this process and you get that k prime of y is a function of x and y, or if you were doing k prime of x and you got a function of x and y, you have made a mistake. Stop. Go back and try to find it. Don't keep going. It doesn't make sense to have x's in a function that's just a function of y, or to have y's in a function that's just a function of x. Okay. All right, but here I did not make a mistake, so we're ready to do step 3. So, step 3, I'm going to integrate integral of k prime of y dy, or if I had started with q so that I had a k prime of x, I'd integrate that with respect to x and put the pieces together to get f. Okay. So I can say k of y is the integral of k prime of y dy. So it's the integral of negative e to the y, which is just negative e to the y plus c. And this is an honest-to-goodness constant. Okay. Now, in this particular case, I was just trying to find a potential function. Be sure you read the directions carefully. Almost always you will be asked to find a potential function. So I don't need infinitely many of them. So I'm just going to choose c equal to 0 to get a potential function. I'm not trying to find all of them. I just need one that I can use in this particular problem. Okay. So I'm able to say that k of y is e to the y. So we had earlier that f of xy was x squared y plus the natural log of the absolute value of x plus k of y. Now I know that's x squared y plus the natural log of the absolute value of x minus e to the y. So we have found our potential function. Fabulous. Now, if we remember what we were trying to do, we were trying to evaluate the integral from negative 1, 4 to negative 2, 5, the work integral that we get with this vector field. And what we now know is that's just f evaluated at negative 2, 5 minus f evaluated at negative 1, 4. So let's see what we get. If I plug in negative 2, 5, I'm going to get negative 2 squared is 4 times 5 is 20, plus natural log of the absolute value of negative 2 is just 2 minus e to the 5th. And then I'm subtracting what I get when I plug in negative 1, 4. So that's going to be 1 times 4 is 4, plus the natural log of the absolute value of negative 1 is the natural log of 1, which is just 0, minus e to the 4th. And I can simplify just a little bit. I'm going to be able to distribute that negative. So I'm going to have a 20 minus 4 is going to be 16, plus the natural log of 2 minus e to the 5th, plus when I distribute that negative, e to the 4th. So that is the value of that particular work integral.